Start, I guess, Maxima. Yes. Good afternoon, everybody. Today, our guest is Francescopaolo Sica, if I am wrong, sorry. And he is the member of IEEE as well, and he will give a presentation on bridging paradigm in SAR image restoration, supervised and self-supervised approaches. And maybe Francescopaolo, you can introduce yourself better than me. Please welcome.
Okay. Yes, thank you very much. I would say I will start directly with the presentation. I know that usually we are short on time so let's leave as much time as possible to questions. Couple of words about myself. I'm from the University of the Bundeswehr in Munich. My previous career was at the German Aerospace Center, had experience at the European Space Agency, and originally I'm from Italy, Napoli, where I started at the National Research Council. So I'm gonna share my screen now, and we start. I believe I hear some microphone from Lakshmi. If like you can close the microphone. Yeah, thank you very much. Okay, very good. So now you should see my presentation and also now in full screen. I'm just reading the chat. Okay. Okay, we will not the chat for now, so let's start. So the topic for today is bridging paradigms in SAR image restoration. We will see supervised and self-supervised approach. I am gonna introduce you what this actually means. So for the outline, I prepared a visual outline. So to get everybody on the same page, we will start from some basics of SAR, and we start understanding what is the actual problem we are trying to solve here. In this presentation, we will see synthetic aperture radar from single image point of view, so which we usually indicate as a single look complex, but also for a multi-channel perspective. And the multi-channel perspective here considered is just the interferometric pair. So we will see classic SAR images and interferometric SAR. We will not take care of other modality of multi-channel SAR. Then secondly, we will see here some characteristic of the signal and what's the problem that we are going to solve. Then we will move to the actual topic. So what is supervised learning and self-supervised learning at this purpose? And then eventually we come to the point of how to bridge the two paradigms. So is supervised learning and self-supervised learning can help each other to improve the state of the art. So we will try to answer this question. This is a very new question and something that is still, there's not much published in this direction. So I will show you some latest result obtained in this direction. So let's start concerning, let's bring everybody on the same page. So synthetic aperture radar can appear in many different ways. I'm showing here two examples. A lower resolution image, a higher resolution image, they look very different. Each of these images is telling us something different. What's the main difference to photography, to optical picture is that we have an active sensor. The basic principle is that we are measuring distances. We are acquiring over a longer time span through a synthetic antenna. And there will be let's say the necessity to bring this echo all together, so a processing that is called focusing to actually generate the image. Why these two images are so different? It's of course the acquisition geometry. We are acquiring a squinted geometry. The look angle will also play a big role, but then also the acquisition parameters. So everything related to the sensor. So what's the frequency band we are working at? What is the resolution? So what is the bandwidth we are using, or what are the acquisition modes? Like if we want to have more coverage or a better resolution, and so on and so forth. We will not go deep into this, but mostly this was to introduce that any of these type of images, they look different from some reason, but they will always, let's say, we will always need to resort to some method to improve quality of those images. So we start from one image. You can understand a little bit the semantic of this image. They look like fields. If we take a zoom here, we see that spatially, even a field is unique, maybe it's the same type of crop that we have in that area. We have this pseudo noise, this salt and pepper noise that is overimposed to our image, to our amplitude image, and it's mainly due to the fact that within a single resolution cell we have different scatterers which we cannot really whose position we cannot really model. So from one pixel to the other, the position of these scatterers will be different, and we can have constructive and destructive superimposition of contribution. So this is actually coming from the coherent nature of the radar itself. So we call this pseudo noise as speckle, and it's something that we want to get rid of for image interpretation, so for improving the quality of SAR images. Similarly, we said through this presentation, we will always have the parallel between a single image and interferometric SAR. We can have two images, at least, to perform SAR interferometry. And also here we exploit the coherent nature of SAR. We will need some sort of diversity, which can be a spatial diversity or a temporal diversity. If we have spatial diversity, we get sensitive to spatial variations, so it means topography. If we have a temporal diversity, we get sensitive to temporal variation, so maybe surface displacement and any other type of displacement we can have on ground. Here on the right side, I'm showing a simple example how to generate digital elevation model without showing the processing chain. The information on interferometry is in the phase difference between the primary and the secondary image. So let's also the INSAR measurement. As we saw before, we had speckle on a single SAR image. The noise on interferometric data is for different reason. It's not the one we have seen before, but it's more due to the diversity itself. So anytime we have a decorrelation between the two images, so the two images don't look exactly the same, we will have some noise arising. So the diversity, which is needed to perform interferometry, it is also causing some level of decorrelation between the pair. So geometrical and temporal diversity is a problem, but then we can also have a problem like the scatter type, like the electric properties or shape of the target, the signal to noise ratio of the individual SAR images, as well as system noise like thermal noise or quantization error. How can we measure this noise? Well, we can measure the similarity between the two images. So we use the coherence parameter, which is the normalized complex correlation between the two images. And this gives us information about the noise level. So where I have more noise, I have a lower coherence, but also the quality of the estimation. So the coherence should also be estimated. And if we have some errors in our estimation, the coherence will drop. So the coherence is extremely important, an important parameter for our for this topic here. So you start understanding that we have three basic quantities: the amplitude of the image, the phase for interferometry, and also the coherence for interferometry. And these are the three quantities that we will try to estimate all over this presentation. So I will show you all the methods we will see deal with these three quantities. Now, let's see also a little bit how the statistics look like, and I will comment very, very briefly on the signal model. The single look complex, so one single image is composed by imaginary and a real and imaginary part, which are both complex and which are both Gaussian and identically independent, identically distributed. So we have a circular Gaussian. So the single look complex is distributed as a circular Gaussian, which also means that the amplitude will be a Rayleigh and the phase of the single image will be distributed uniformly. When we get to the INSAR pair instead, so we have the complex product between the two. The phase of this complex product is called interferometric phase, so it's the information on in our signal. And then we also define the coherence as an estimation of the in amplitude and phase of the complex interferogram normalized for the two amplitudes of the two single look complex. The absolute value is what we call coherence. The old parameter we call complex coherence, and the phase is again the interferometric phase. And this is also described by this matrix here as a bivariate Gaussian, where R1, R2 are the real reflectivity behind the noisy amplitude that we measure, and R1, 2 here is the geometric mean between the two. So in both cases, I'm not writing here, I'm just saying it orally. In both cases, we have that we can express the noise as additive. In the case of a single image, so in the case of speckle, we can transform in log domain, so go in an homomorphic domain, and we have an additive model noise, otherwise model is usually multiplicative. And in the second case, we can write the noise as additive and signal dependent. So in both cases, it's it's an interesting problem to solve from the signal processing point of view. So let's see how this is classically made, and let's see why we need still to refer to this classical estimator. So what comes to the estimation of the best scatter, we can take local averages under the hypothesis is that the pixel, so the values of amplitude, of intensity that we are mixing, are within a window in which all the pixels can be considered from the same statistical family. So we usually talk about local stationarity, so meaning that each pixel should be drawn from the same random process. And under this hypothesis, we have the maximum likelihood estimator that was derived, and it works very, very fine. Very interestingly, the variance of the estimator scales up, is inversely proportional to the number of looks. So how many pixels we consider. Similarly, we have something for the estimation of phase and coherence. So we can average spatially, and in this case, the hypothesis is a bit more restrictive because we need the stationarity. Here I write out the interferogram in general, but actually we need stationarity of all the processes involved here, which is the complex interferogram, but also the single intensities. So it's even stricter, the hypothesis that we need on in the case of interferometry. But if we have a window in which this hypothesis is respected, then we have an excellent estimator of coherence and phase, and the variance of the estimator also scales up with the root of L. So additionally, the coherence estimate is biased for low number of looks. So the number of looks is a very important parameter here, and we should always keep in mind when we change method to what is the number of look, because it gives us two things. So here, the variance of the estimator, which scales with L, and also here we'll have a dependence on L and the coherence. So it means that once we estimate properly the coherence and we have the number of looks, then we can derive how accurate it was also is our estimator. So it's an incredibly important parameter. And we also notice that we want this L being as large as possible. Still, we have some limitations. So this is not as easy as it looks, because we want to preserve spatial resolution. So local stationarity, it's easy to say, like it's an hypothesis that is extremely simple, but at the same time, it's very hard to be met. Indeed, like let's take some random image, you can see that we can smooth out the image with growing windows, and then we see that we are losing resolution. So we increase the number of average pixels, so the number of looks, but at the same time, we are reducing spatial resolution. What means that for the speckling, we are reducing the resolution of our image, which thing that we really don't like, because we like to have sharp images and without noise. And secondly, we also get some radiometric resolution loss. So the level or the amplitude is not anymore preserved. For example, we have point scatters that are very, very bright, and this will be spread all around the image for a higher number of looks. And in the interferometric case, instead, we can have a blur or some broken fringes, plus we have a coherence drop, because once we mix together contributions that do not match the same statistical process, then we have also coherence drop. So first problem, spatial resolution. But since we are considering also the interferometry application and all the data that and all the product that can derive from it, we should also consider another type of resolution, like the resolution elevation. Let's say the case of generation of a digital elevation model. We want to be as much as possible sensitive to changes in elevation, and therefore we have this formula that helps us. So the orthogonal baseline is basically the distance between the two satellites, and here we can see, in order to increase the phase variation independent, like depending on the variation of the elevation, then we need to decrease the height of ambiguity, and therefore, if we take this other formula, we need to increase the spatial baseline. So we move from P1 and P2 that we see here to P3, P4. This is an exaggerated geometry just to make you understand. The larger it is, then we will have denser fringes. So this means that if we want to increase the resolution in the elevation, so we want to get more accurate digital elevation model, we will also have to deal with less stationary patterns. So this makes a big challenge in interferometric case. So now let's move to how this was solved in the past. I do not intend in this presentation to provide a complete state-of-the-art of what was pre-deep learning and what is today deep learning, but I want to show you the main concept behind those. So just a couple of words before the deep learning took the scene to classical filters. We had a way to deal with this non-stationarity. For example, directional filters, like the leaf filter was preserving edge and corners, because we select the best direction in which we can smooth our data. Then we can have non-local filters, which generalize this concept to a filter of any shape. And then we also have transform domain filter, or even combination between transform domain and non-local filters. This was the state of the art before deep learning. And interestingly, for all of them, it was possible to derive a number of look, and therefore more or less the quality of your estimator. And also very interestingly, all of this were requiring a minimum amount of user interaction. So if we want to use today's language, basically we had no supervision. So let's move now then what is the actual state of the art, where deep learning is ruling right now. We can have two main type of approaches, supervised learning and self-supervised. We start from the first one now. So to provide you an overview of what supervised learning is providing, so generally we need some labels. We have noisy measurement as input, and then we have some labels as output. So this means that we should create a dataset, our own dataset. Very possibly, if we need labels, we will start from generating our own fringe patterns or generating our own SAR amplitude and superimposing some noise to generate our input to the network for training. And the noise is model-based. So we need the signal model for the different approaches, as I was showing you before, and we need to generate a synthetic dataset. In addition, we do not lose generality with this graph when here in the middle, we just talk about convolutional neural networks, and we also do not lose generality if we even more specifically talk about residual unit. So, of course, not all the paper are using it, but most of the paper and the residual unit has been shown to work very well. And very interestingly, in order for you to understand better the state of the art, when we look for it, is very often in supervised learning, the basic approach have a link between input and output, meaning that I'm copying the input to the output. The output of my network is actually my noise, and I'm subtracting noise to my input. And here I get my clean data. Of course, the network is then optimized to get the noise-free labels that we created before. So this is a general scheme that is is valid for the speckling and for interface and coherence estimation. And what we need to keep in mind here is that we need the large knowledge about our data, and this data should be close to the model that we use for the synthetic dataset. Let's bring some examples. Again, by no means this intends to be an exhaustive state-of-the-art review, but I will provide reference afterwards for the interested one. Here I derived from these two papers. In the case of the speckling, there are several methods, and multi-objective despeckling proposed in this paper here is also working very fine. And what they are doing is mostly they start from SAR image, which can be retrieved from multi-temporal stacks, and then they superimpose their noise, and they try to let's say all these methods are more or less based on this concept here. For what concern the phase, we have more or less the same. So the FINET, I will introduce it a bit more in the specific to provide you some more details. And INSAR Monet was trying to improve the FINET result by introducing some further constraint in the way the network is optimized, and these were shown that the result is very comparable and very often even superior to former state-of-the-art these are two non-local filters for interface estimation. So now a couple of words about the FINET. That was the first supervised approach proposed in this direction, and the fundament of this approach is basically to provide system knowledge to the network. And this was done in three ways. So we need a noise model. So this is the way we generate our data starting from noise-free data. Then we have to model the noise-free parameters. So everything, amplitude, coherence, and phase have to be modeled somehow. And then furthermore, we need to decide how to pre-process and post-process our data. And this is fastly made in this way. So for what concerns the noise-free parameter modeling, we had to consider every type of variation of the phase, so a flat phase or with some fringes. And for what concerns the amplitude and coherence, we had to understand, do we have any degree of correlation or not? So we do not only need smooth or abrupt changes, but we also need to consider if we correlate the different noise-free parameters. And then the noise model is the known one I showed you before. And for what concerns that pre-processing, we have an input. We usually separate in real and imaginary part the complex interferogram, and so this is the same that we try to retrieve as at the output. So some results: the FINET was performing way better than non-local filters on synthetic data, as well as also on real data. Very interestingly, here is a scene over an airport. We see there are that can be, this is of course not the same date, the optical reference, but there can be some targets. This could be airplanes or some other vehicles on this ground, and you can see that the FINET was really able to find this target in the coherence map. So performance are very, very good here. Very interestingly, where the coherence is low, we are generating some fringes, and these are artificial fringes generated by the network, and this is already the first risk we have. So this is network hallucination. Of course, it doesn't create too many problems because the coherence is low, and we know that where coherence is low, we know that the interferometric phase is not a reliable measurement. So it's not a big problem for applications, but still, why do we have this? And it's something that we really do not want to have. This is, of course, this came out from how we created the data set, because sometimes strong noise and high fringes, like it can, the noise can create some aliasing. So it's basically a wrongly sampled fringe. So these cases should have not should have been discarded from the dataset, but this will always happen because combination of data are very vary. So, but this would be something that would be nice to not to have, and it's strictly related to supervised learning. So let's see some things that we like from supervised learning. We have excellent performance. We had obtained performance better than state-of-the-art. Processing time is not a problem. After training, the inference is very, very fast. We have an opportunity to inject any physical model. Basically, we have a model, we create our data set, and this is the way to go. It's easy to apply to different type of data, like just changing the training data set. So it's also very, very flexible. What is that we don't like? So the output is strictly dependent on the training data set. So everything that we didn't generate in the training data set because we forgot or because we didn't succeed, then we will not find it in the output. So we can have missing features due to the fact that we missed them in the simulation, but also the statistical model. This is the main problem that could happen. The statistical model of our real data do not match maybe what we generated. And this has happened also in my experience at DLR when we tried it from when we went from satellite data to airborne data. In some cases, airborne data were very special. Even for SAR expert, they could say that this was not the usual in-SAR noise. And in this case, of course, it was not working. So there is some work to do in that direction for adapting it. Then we have possible unwanted artifacts, like these artificial fringes that were generated in low coherence area is something that we do not want to have. And the biggest concern for SAR experts here was, what is the number of looks? I was often asked, what is the number of looks? How can we compute the variance of the estimator? How do we interpret the result? And this is actually not possible, and that's why in this sense, this deep learning approach was labeled as a black box approach, even though we know what is happening there. The number of looks, it is not yet possible because, like, when they ask, okay, there will be some average involved. Well, the latest result is obtained taking the input and subtracting from the input, subtracting the noise. So there's no real average on the result. So these are all things that then drives us towards the self-supervised learning. And let me introduce you briefly self-supervised learning, why this has taken growing as such a growing importance in the recent years. So self-supervised learning was it's not something strictly related to denoising, but for representation learning was this used. Like let's say we have in mind a given downstream task, which could be, for example, image classification. And we want to pre-train our network so that the network is... I got a signal that my internet is not stable, so just give me a thumbs up that everything is working, please. Maybe Füsun or Junichi, you can give me a thumbs up that everything is working. Excellent. Thank you very much. So self-supervised learning was created for this. So I want to do image classification, but I want to pre-train my network in a way that the network already learns useful representations of my signal. So that means that I have, for example, here natural images, and I want to feed my network with these images so that some feature get extracted, which are already feature taken from my dataset, even though I'm not solving my downstream task. But like the way I can do it is to find a pretext task, and a pretext task could be I add some rotation to my image. I know what was this rotation, so I feed the new image and I try to output, I try to regress like how much was the rotation in my image. This is just an example. Similar things can happen with flip, can happen with color change, and so on. So these are all tasks that I do not need as final user, but It's something that the network is doing and is learning how these images look like. Then I can move towards my downstream task by freezing part of the network. Here we see, for example, we freeze the first part of the network and we are changing the final part of the network in order to output the label we want. So it is shown that after learning representations, the downstream task is much easier. It's better performance and the convergence is much faster. So this was the main thing. And then this became bigger and bigger till today. We had a rebranding of self-supervised learning, which is foundation models now, and it became larger and larger on larger data set, any modality, and so on. So this is a very modern topic, let's say. How do we use this for denoising? This is more or less something that we are misusing in a way, but we have different ways. For example, we have approach like the noise to void, noise to noise. I'm not mentioning now the single all the possible approach in this sense, but I want you to remember that we have that we can have, for example, blind spot networks like classical convolutional neural networks works in a way that we have a receptive field and then we perform a prediction. Since we are using only noisy data from the same image, then we may want to hide the central pixel. We see just the context, so the pixel around it, and we want to estimate the central pixel by using as a label the noisy one. So this is a way to go towards self-supervised learning, but we have also other ways to perform this, and I'm showing it to you here. So we can have, for example, let's consider just the amplitude case. We want to go from a noisy amplitude to the other, to an estimate. And in a training stage, I can use two independent noise realization of the same area. How do I get them? Well, this is up to you. This is up to what the actual algorithm is. Some people were using sublux to generate different noise realization from the same areas. Some other people were using real and imaginary part of the data, as I will show you very soon. For what concerns interferometry, we have the same pre-processing. We feed the real and imaginary part of the network, and we need to have like a map that has the exact same interferogram, but with a different noise realization, which is also independent from the input. So this is a bit more difficult to obtain. Now I will mention what is in the state of the art. You will notice here, again, we can use an encoder and decoder architecture without losing generality. Of course, I do not exclude the fact that generative models were used and more recently even transformers, but this is not about providing, let's say, all the state of the art, but more the concept behind this. We do not have any link between input and output, because otherwise the network will simply output zero noise, because we are able to fit one-to-one a noisy image. So this is a thing that you should keep in mind. The labels are noisy labels, and the loss can be any loss that can deal with the type on which we are considering. On top, we said we can have blind spot networks, like we can use a masked input, like where you see this black spot, we are masking out these pixels. And on the other side, we have a masked loss. So we are computing the loss only for those blind spots. The convergence will take more time, and we will see that this is not ideal in the interferometric case, simply because of the fact that we need that the different samples are uncorrelated, so spatially uncorrelated, which is an hypothesis that in SAR usually is not like this. So let's see some state of the art. I was mentioning before the Merlin, like this is in this moment, this speckle to void and Merlin were the two self-supervised approach that best performed on amplitude data. They compared also with a non-local filter, the Sarbian 3D, and they showed how nice were the performance in these cases. I will go through the Merlin approach soon, just to explain you what's the criteria behind. And for interferometry, here we have a comparison with the FINET we have seen before, so a supervised approach with another, INSAR Monet as well, a supervised approach with a new approach, the INSAR to INSAR. Here we see this one was trained on Sentinel-1 overlapping data. So on the overlapping area of different bursts of Sentinel-1, where the author says, under given circumstances, you have in same interferogram and independent noise. We know that it's not exactly like this, so a big check on this overlap area should always be done. But they managed to perform some training. Of course, there are some drawbacks that I will explain later. But still, they got an algorithm that is quite comparable to state of the art. Then what's our real feature or not? This is everything to be understood. And the coherence instead is a bit lower than what is to be expected. So it's not a great estimation, as the author also specifying this paper. Then let's move to the example I was telling you before. So self-supervised learning for the speckling, the Merlin algorithm. Here we had, very interestingly, we said we need 2 images with of the same scene and with the same type of noise, but independent realization of noise. This means that I can use from a singular complex real and imaginary part. And real and imaginary part, as I told you before, are independent and identically distributed as a Gaussian, and the authors found a way. So the explanation here is easy, but the author found a very rigorous way to come up with a measure to provide then the speckled image. And what we had here was like we train with one of the 2 real or imaginary part as input, and the other one is used as a reference to estimate the intensity. At test time, we have then a prediction that is the average of the 2 predictions. And result I showed you before are excellent results. So self-supervised learning for the speckling has been proven to be very effective. And now we move to the case of interferometry and blind spot, just to show you, in addition to the previous result, that also the blind spot have some problems here. If we have on the left 2 different patches of noisy data, the maximum likelihood on a very small windows tells us it's more or less a reference at low resolution. Then we have state-of-the-art filters which provide a very nice smoothing, and at the same time they preserve details of fringes and so on. And the blind spot instead has still some problem in denoising, so the denoising power is not that high. And furthermore, when we look at the coherence, we also see strong bias. So the insert to insert showed a bias towards lower value. Here we see a bias towards higher value. So the coherence problem has not been yet really solved in this case. I will mention one more algorithm actually that might be solved this. So in general, we have that supervised learning show generally more stable performance. So it's something that we can probably rely more on, but still self-supervised learning is something we trust more because we just use real data. For what concerns the speckling, the self-supervised learning was excellent. For what concerns interferometry, there is still some research to do, like for example on the coherence estimation. And let's talk a little bit about the different methods. We had the insert to insert. This was trained exactly on top SAR burst on the overlap region. These are possible only at low resolution. So it's for sure there will be some problem in filtering, for example, high resolution data like from TerraSAR-X. Then we have an algorithm an approach that I'm just citing now for the first time, the Mucha Pro, which is transforming the covariance matrix taken from the usual complex covariance matrix from interferometry to a real valued covariance matrix and applying the Merlin approach on each of the component and then transforming it back. This is probably the most promising at this moment for estimating phase and coherence, even though this strongly depends on the use transform, and at the same time, the amplitude values can be seen in the coherence. So there are some also here, I wouldn't call them hallucination, but it's more an effect of the transform that could mess up a little bit coherence values. In my opinion, probably since we do not have an excellent approach, an excellent way to go for self-supervised in INSAR, the Mucha Pro is the best approach right now. And then we also have seen the blind spot networks, which have strong, really limited denoising capabilities and also large coherence biases. So now I want to show you one more thing, since before moving to next topic, is since self-supervised learning was introduced in representation learning, and then we use for denoising, actually now the trend is also going the direction foundation models and so on. How do we learn representation from SAR? Therefore, we are again doing the step on the other way around. Like, is this task of denoising, like, for example, let's consider the Merlin approach, is this useful for other downstream tasks? So is denoising helping us to create useful representation of SAR data? Well, the answer is yes. There are several approaches popping up in the recent months. It can help other regression problems, for example. It can help length over classification, or for example, even image compression, like SAR image compression. This last case is something that I show you here, and I want to show you. So the training, we take a basic network for neural compression, and this network is trained for this speckling according to the Merlin approach. So we again have real or imaginary part, and we try to estimate intensity. And in the middle here, the bridge, in the bridge, we also have quantization, arithmetic encoding, and then we get a bit stream. And we showed, very interestingly, that performance are excellent and are even superior to the simple, to the sole Merlin approach when performing this speckling and compression together. And we also show this here, like the results on the peak signal to noise ratio. We always get a better result for whatever is the ratio, the compression ratio. This means that actually the two tasks, not only the speckling is helping to learn useful representation for compression, but there's also the other way around. Like the compression has also improved the speckling, and we show this in this paper here. So self-supervised learning, it's very interesting also for this reason. And now we try to understand how to bridge the two paradigms. So the question here is, very briefly, could one combine the two approaches together? Like, let's try, for example, the most trivial approach to this is to refine supervised learning methods with self-supervised learning strategies. So, for example, we had before, this is something I'm showing mostly for interferometry, because interferometry is the challenging topic here. For what concerns the speckling, we have seen that we can actually use self-supervision in place of supervised method. So let's take, for example, the FINET or any approach, any network. We do not have any connection between input and output, because then we want to use the self-supervised approach. And we train this network in the same fashion that we use for training the FINET. And we have a first training and a first network which is able to perform these operations. And then we decide to retrain maybe the whole network or part of the network in a self-supervised way. Like I can take some real data feed it to the network, and like we can take any self-supervised approach, like it could be the blind spot, it could be like the one used in insert to insert, and we try to iterate in this way to get also out of curiosity to understand how the result look like afterwards. So we start from the FINET, we use the blind spot method here, and we get these results here. So just to show you, the boxcar image here is used as low resolution reference of a semi-good estimate of the face, so we can understand the structure a little bit. This was the estimate that we get in the from the FINET, and then I extracted from my training three different results to show you where are we heading to when we use real data. And very interestingly, somehow we see, for example, here, this area here, it's something that is this is a lake. So somehow we are getting again from the result of the FINET towards something that we were getting in the real that we were getting by using self-supervised learning. So we are somehow improving the fact that we want to flatten this watered area, but at the same time we are sometimes estimating differently the fringe, which is also not good. Then this estimate looks more or less similar to the FINET. The other one is introducing too much noise. So we do not really have control about how much noise we are reintroducing, how much details. And furthermore, when we observe the coherence, for example, then we have, again, boxcar and FINET. We show here that we have a nicely estimated coherence map, and we have some degradation of the coherence while we were believing that we were improving the phase estimation. So this means that, first of all, it's very difficult to get a good estimator of the phase and of the coherence in this self-supervised approach. But furthermore, this also tells us where to stop. So what criteria can we use to stop training? So this doesn't really feel like we could get some good results and also try to validate with data, but it doesn't feel like a rigorous scientific approach. Therefore, we dropped it and we started reasoning in a different way. So with Loïc Dennis from the University of Jean Monnet of Saint-Étienne, we were thinking to just alternative schemes of self-supervision. Like, for example, how can the SSL bring us closer to classical filters? We said before, the number of looks. Can we try to understand better the number of looks? Can we try better understand how accurate is my estimator? Is my deep learning model hallucinating? Is my deep learning model bringing me away from something that is accountable? So how can we make the deep learning model more accountable? Well, we decided to transform the data in a way that we get the ability to test some estimator properties. So we can have any type of estimator, which could be the maximum likelihood approach, it could be non-local filters, it could be a deep learning approach, and then we feed them everything to the same processing chain, where we start comparing model plus transform and the reciprocal, and then the other way around, like first the transform and then applying the model. For example, here I just providing one type of transform. INSAR is invariant to phase shifts. So we know that an interferogram, if we sum up any offset, will have the same information. Therefore, our question is, this is a very simple example. If INSAR is invariant to phase shifts, then also the result of our estimator should be invariant to phase shifts. So this seems trivial, but it's absolutely not the case. And what we compare, I'm just providing you some example here. when we will compare in the following case A and case B. In case A, we first apply the model and then apply the phase offset. In case B, we first apply the phase offset and then the model. And let's observe some results, for example. So we had the maximum likelihood estimator. Here we use a 9x9 boxcar window. In case A, we get this map. In case B, this other one. I go back and forth. There is no change, as it is to be expected. So there should be no change in the two cases for the maximum likelihood estimator. And that's why also this estimator is so reliable and still used today in many SAR processing chain. So we have 0 error. Then let's go to the FINET. This is the case A. Then we move to case B. I move back and forth. We also don't see any change here, and we get 0 error. Why we get, in the case of FINET, 0 error? Because when we wrote the signal model of the FINET, we also took into account that there is correlation between real and imaginary part, which depend on the phase. Therefore, we made the work in making the FINET robust to phase changes, to phase offsets. So that's why we get no error here. But this is absolutely not trivial for any deep learning model. Like, we get state-of-the-art supervised learning is the INSAR Monet, and this is case A and case B. So you see some changes. And I tell you, if you give me the first one or the second one, I will tell both are good estimate on my phase. But why do I get two different ones? This has no sense. This has no meaning. And this also means that I wouldn't rely on a deep learning model that has this behavior. So I get a result that is departing from 0 error. I already know here that I should watch out the results of this model. And yeah, this was, let's say, the simple example that explains you the logic on which we are working right now. So what I showed you, there are mismatches between deep learning models and classical methods. So when the SAR expert look at the deep learning model as a black box and saying, I can't rely on this, well, he's right. And we are trying to understand these mismatches and to make these deep learning models more reliable and accountable. So what I showed you was a simple example. This is not the only possible transform. Interferometry offers different opportunities to manipulate the data. And the next question will be, can we use this logic to perform fine-tuning of supervised learning solutions, or, for example, performing self-supervised learning through these rules? The answer is yes, but it's coming soon, since this is all work that is going on in the recent months. So takeaways: both supervised and self-supervised approaches have shown valid performance. I showed this to you. The speckling for the self-supervised learning is basically with the Merlin approach is state-of-the-art. For the INSAR estimation, there is some more research to perform, and this work that I'm showing you today is something that goes that direction. Achieving the best from both worlds by combining the two, it's actually might be not that trivial, because we lack a little bit the measure of the best performance. But what I was showing you before is also a way to do this. So we can use self-supervision in other ways, like, for example, enforcing some properties on the estimator. I'm providing you also some reference. Recently was published this book edited by Michael Schmidt and Ronnie Ensch, where also you get 2 chapters on deep learning for SAR amplitude despeckling and deep learning for INSAR processing, which actually describe this exactly the topic of today. Just to say it, I don't get any money or any reward from saying this, but in these 2 references, you will find all the references about all the algorithms that we spoke today. Thank you very much for your attention.
Thank you, Francescopaolo. It's really a very nice presentation. We learned a lot, and I see some questions for you. Can you see them, or would you like me to read it for you? It is in question and answer part of the Zoom.
So in the webinar chat, you mean, right?
Yes, on the
Okay.
bottom of,
So I
yeah.
see many people saying hi. So this is one.
No, it is just there is it's not the
Sorry.
it's
You
a question and
oh,
answer. Yeah.
oh, good, excellent.
Yeah.
So we get okay. I will start reading and then answering. I see that it's 3 minutes to 2. We can proceed
A
further
few,
later.
a few minutes
Right?
more
Okay.
we can have.
Mhm.
We can try
Yes.
to answer. Thank you.
So
If you have time.
I have
Yeah.
time. That's absolutely no problem. Okay, so the first one is how to understand a movement towards and away in the fringe of interferogram image. I will try to answer probably first the questions related to the actual topic, and then I will go back to those. Okay, how to get freely SAR data, same for NVSAT and TerraSAR-X. I believe this is also not that much related to the topic, so I will jump this one too. We get a long question, a bit out of track too. My research team includes wetland change detection and vegetation in it as well. I'm implying SAR, I can't find a way around it. Incoherent decomposition is more applicable for distributed targets, such as vegetation, wetland, and coherent decomposition. I believe this is also out of the talk. The difficulty is established. Okay, maybe the best way is to that I respond offline to this, and I check, is there any possibility to transform SAR to RGB, since SL algorithms are promising results in downstream tasks like land use, lane cover, image classification. Do you think this approach can give better results for the target task if you integrate the transformed image? Okay, these are, I believe, a bit all out of topic questions, but we can anyways, you tell me, provide an answer now if or simply we will proceed offline.
As you wish, maybe. Okay, these are not direct questions to your presentations, but probably
Yes. So maybe I can
pro
answer very quickly to each of those so that everybody's happy.
yeah.
So how to understand the movement towards and away in the fringe of the interferogram image. So this will depend on what is your master image, and you will follow if the phase is going down or up. I will say to answer very quickly to this. Then second question was how to get freely SAR data for NVSAT and TerraSAR-X. I believe that ESA is providing some NVSAT and TerraSAR-X data. So creating an account there is always a good idea, and you can download some data. Then we had the use. This was wetland change detection. So here I should actually, there's no question mark, so I will try to understand what is the question here. So we have incoherent decomposition is more applicable for distributed targets, such as vegetation and wetlands, than coherent decomposition. But sir, incoherent decomposition is based on eigenvalue, eigenvector, the difficulty in establish relationship between eigenvector and physical scattering mechanism. The emphasis, yeah. What's the question here? Maybe you could phrase it in a question, and I will answer to you. And then Tugba is asking me, very nice to see you here. We have met a couple of times. Is there any possibility to transform SAR to RGB? Well, if this is your main goal, there is plenty of literature in SAR colorization. So if you're interested in this, like maybe a keyword for you is SAR colorization. I don't know if this is 100% useful to your research because you motivated that SSL algorithms are promising results in downstream tasks, image classification, and so on. Do you think this approach can give better results for the target task if you integrate the transformed image? Well, I believe instead of, if your final goal is land use, land cover classification or general image classification, I wouldn't really look into the colorization of SAR data, but I would rather try to perform SAR representation learning, like for example what I was explaining before, denoising in a multitask fashion, for example, can provide you useful feature also for other tasks. And I'm sure you will notice some improvement in the performance. And if it's not after many training epochs, for sure you will have a faster convergence of your network. So this is a way you can try out. I got a fifth question in the meanwhile. Do you think we could reach a point in which we could safely process the interferograms with this speckling before applying a time series analysis, at least in terms of having better fringes to reveal the physical signals? Or would it hide underlying physical signal? I'm not 100% sure I understood your question, but before the time series analysis, interferograms are like the interferometric phase and coherence is estimated. So the new stack is based on estimation of phase and coherence. The coherence is used to find usually reliable pixels. Then it changed a little bit depending on what application you are pursuing, and then the interferogram is estimated. So these are not noisy interferogram that are used there. If I didn't answer your question, you can write here. And I believe we are done with questions, right?
I think yes, it's all the questions are covered, I guess.
Perfect.
Okay.
Sorry, there are some in the chat. I don't know if you have already addressed.
The chat, no. I see some. Okay. Let me see. To which one exactly are you referring to?
I'm referring to the one by Herschel that says like, how can supervised and unsupervised SAR classification be applied to soil moisture mapping, flood detection, or urban monitoring?
So this goes again into the direction of applying like for other downstream tasks. So the talk was mostly on estimation of parameters, but as I showed you, self-supervised is going into the direction of representation learning as it was first introduced. And you can also try to perform denoising tasks and in parallel also the downstream tasks that you want. This is one way to go, which could be could be nice to explore.
Yeah, there is one more, sorry, last one, I think, and we can wrap up. It says, how generalizable are models trained on one SAR platform, for example, Sentinel-1, when applied to data from different sensors with varying resolutions and wavelengths?
Yes, this is an excellent question. Thank you very much. And usually generalization is not working across different sensors. So you usually retrain for every specific sensor. We showed that for supervised learning, it was a very general model. So it was more or less working for mid to high resolution sensors. Therefore, we trained on Sentinel-1 and on TerraSAR X, and it was working anyways. For what concerns the like the other question was, self-supervised learning, then there probably you want to use the specific data and retrain on the specific data of that sensor. But usually generalization is a big issue in this case. So especially in the case of self-supervised learning, I would retrain my model.
Thank you so much. Now I think we should stop taking the questions. It's already 5, 6. Okay. Over to you, Professor Füsun.
Yeah, Laxmi, I think we couldn't cover all the questions in chat box, but it's already more than 1 hour. What do you think? We should finalize this session or continue?
Yes.
Okay.
Yes, what I can tell, I will also leave my email here.
Yes, please.
As I showed at the end. So if there is any offline question, we can keep chatting in this way. Yes, this should be correct. Perfect. I don't know if everybody can read this.
I'm
going to share it. No, actually it's only to host and panel, so I'm going to share it to everyone.
Okay. Yeah, I also share it again.
Yeah.
Perfect.
Okay, thank you very much for this nice presentation. We learned a lot and hope to see you in Canada in ISPRS meeting.
This will
Thanks
be
a
nice.
lot.
Thank you very
Thank
much
for
for having me here. Thank you very much for everybody that attended and also for the many questions. See you in Canada.
Okay.
Thank you so much, Francescopaolo. Bye bye.
Thanks. Bye.
Bye-bye.
Thank you, everyone. Bye.